Hello everyone. In this session, I am going to talk about how we can really use boosting for classification purpose again. But in this case, the classification that we are talking about is where the response variable is a multiple category. So in the previous session, we looked at the classification case where the response variable is binary. Only two categories are there. So here we are considering the classification case using boosting where the response variable is having multiple categories. And in this context, we are talking about three different algorithms. The SAM algorithm, we are talking about the Bremen's extension and Freund's adjustment. Again, these are the three which are majorly targeted. These three can be used either for binary classification as well or also for the multi-category classification. Just that I want to give you an exposure to different kinds of algorithms. I wanted to cover these three with a separate set of algorithm altogether. And remember, these are all different kinds of extensions to the AdaBoost algorithms. Small changes done to those AdaBoost algorithms so that they can be extended to multiple categories as well. So again, we will be taking a data set, the same training data, same testing data for all the three models. We can run the model with one of them, make the modifications for the second and third, and try to test them out on the test data to see which models are giving what kind of accuracies overall. So the data that we are considering for this purpose is the vehicle data, right, which is there in this particular location. I'm loading this vehicle data, looking at quickly the attributes of this. There are 634 rows and 15 columns in this data. And looking at the quick summary of this vehicle, so these are the things we are interested in looking at the class of the vehicle. This is a multiple categories, right? We are talking of 218 buses, 217 Saabs and 199 vans. So this is the class which happens to be the response variable for me for this model. We want to see if we can try to build a relationship between the class of the vehicle and the various attributes associated with the vehicle like compactness, circularity, distance circularity, radius ratio, scatter ratio, elongatedness, maximum length aspect ratio, few of the various parameters that are associated with the vehicle. I really want to see if I can link the class with these various attributes. What is the level of accuracy for me in terms of predicting the class of the vehicle given the various values associated with all these different attributes. That's the objective with which we are going to work with. So this is the data. Alright. Now let's look at the algorithm per se. SAM is, so basically we are using it for multiple. So we are extending the binary AdaBoost algorithm in such a way that it can cater to two or more classes. If you look at it, it will still use the exponential loss function just like your AdaBoost M1. Look at this, the alpha M, which is the iteration specific coefficient. Here also log 1 minus epsilon m by epsilon m plus log k minus 1. This is an additional part that is getting added. This is more for adjustment per number of classes. If you set k equal to 2, which is binary, log 2 minus 1, log 1 becomes 0, and your weightage is simply becoming log of 1 minus epsilon m by epsilon m, which is exactly same as your AdaBoost M1 model. So this is where we say it's an extension. Based on the number of classes, number of categories that we have as a part of the response variable, this would get added to the overall weightage specific to the iteration. So that's the difference between the SAME algorithm and the ADA boost algorithm, right? So by setting k equal to 2, I can very well use it for binary boosting, and if k is greater than 2, the same would get translated into a multi-class boosting kind of a model. So it is executed through the package called AdaBag, right? AdaBag is the name of the package, and the boosting is the name of the function with which it goes. So let's try to look at the AdaBag package and the boosting function. What we would be seeing is the same function from the same package would be used for all the three models that we are going to discuss in this session, right? With small changes to this boosting, especially the coefficient learn. This would change between all the three models that we are going to take up. Once I open this up, you will get a clarity regarding this. So let me do the installation of the package AdaBag. This is the name of the package that we are installing out here. Okay, it's installing the package. Yes. Now let's load this AdaBag package. Alright, all these things it requires RPAT again, where we can set the controls regarding maximum depth of the tree, complexity parameters, the minimum number of splits, all those things. Now, apart from that, it also uses a few other functions. Even caret it uses, MLbench it uses, ggplot2 it uses, various other packages also it is using. Now, what we want to look at is, I want to use this boosting function. So let me see what contains as a part of this boosting. So in the boosting function, you could see here, applies the AdaBoost M1 and SAME algorithms to a dataset. That is what is this typically doing, right? Within that, some kind of small modifications that I can give. Fits the AdaBoost M1 and SAME algorithms using classification trees as the single classifier. So the single classifier or the weak classifier is still the classification tree, but it starts learning from those classification trees and it fits the algorithms accordingly. Now if you see boosting, the formula we are giving, where we have the vehicle class as the dependent variable or the response variable. All others I can take them as explanatory variables. The data I know. Boost is a bootstrap sample of the training set drawn using the weights of each observation on that iteration. So if I want to, by default it is set to true. So which means it's a bootstrap sample of the training set that is drawn using the weights for each observation on that iteration. So different weights are applied for different iterations, and based on that a sample of the training data is being drawn for fitting the model. M final is a very important term out here. It's an integer indicating the number of iterations for which the boosting is run. So this is by default it is 100. So I have to set how many iterations it needs to perform. And as I have highlighted earlier also, too big is also, too many iterations is also dangerous. It may result in overfitting. Too little number of iterations is also dangerous. It may result in underfitting. So we may try to understand, we may try to work out in terms of what is the optimal, right? I will try to come out with what is the optimal number of iterations that need to be executed We will do a cross validation kind of stuff, and we'll try to arrive at what should be the optimal number of iteration. Initially we can set some number of iterations and we can progress, then we can make the modification. So M final talks about how many iterations you want to go ahead. Now here comes the coefficient of learning. The coefficient learn, if Bryman is by default. So based on that, the alpha value will be set. Alpha is the weight associated with this coefficient, with the iteration specific coefficient. So based on that, the alpha is communicated as 1 by 2 times log 1 minus error by 1 minus error by error. So it is typically computed that way, right? If it is Bryman, which is going to be the next one, 1 by 2 times 0.5 times log 1 minus epsilon m by epsilon m. So this is what actually happens in case of Bryman. If Freund is used, if I am using Freund, that is what is our third model, 1 minus, so this half will not be there. The alpha would directly be 1 minus epsilon m by epsilon m. That is what is the alpha that is taken in case of Freund. In both the cases, AdaBoost M1 algorithm is used, and alpha is the weight of the updating coefficient. On the other hand, if this is set as ZHU, that is what we are going to set now. The SAME algorithm is implemented with alpha as log 1 minus error by error plus log n classes minus 1. This is the one. So if it is Bryman, this term will not be there and this becomes half into. And if it is Freund, even this will not exist. It simply goes like log 1 minus alpha m by alpha m. So that is what are the three models that we are going to look at. The controls, yes, I want to set the R part algorithm if I want to change the controls with respect to the maximum depth or complexity parameter or the minimum split or any other things. So with this we have to go ahead in terms of fitting the model. So which means we are building three models. First we will go with a ZHU model. We'll set the coefficient of learning coefficient as we'll set it as ZHU. After that we'll set it as Bryman and Freund. That's the only difference between the three models that we are going to discuss in this session. Right? So now let's see whether we can get started with the model. Load the AdaBack package. Done. Get the necessary data into R. The response variable should be a multi-category factor variable. And we know that it uses R part for the control. So if you really want to set some kind of specific control, just for understanding, if we recollect R part dot control, these are the base controls that it sets. Minimum split it sets at 20. Only if there are at least 20 observations in a particular node, then only it will be considered for further splitting. The complexity parameter is set at 0.01. So any split that does not decrease the overall lack of fit by this much will not be splitted. So minimum it has to decrease the overall lack of fitment at least by this much, then only the splitting is going to happen. So like this, the maximum depth of the tree is 30. So if you really want to reduce it, you can very well reduce the stuff or you can very well increase them. So these are the defaults. So for for this case where my objective is to explain you the whole concept, I would like to go with the default implementation of rpart.control itself. So I am not making any kind of modifications to the rpart.control. Now split the data into a training data set and a testing data set. Yes. Overall, how many records? I have 634 records. So out of that 634, 70% is 444. So I will do a setting of a seed and I'll create a variable called train, which is sampling between 1 to 634 some random 444 observations with a replace equal to false, no duplication. Based on that, I've got my train data. So based on the train variable, I'll create my train data, which is nothing but it's a subset of what is this vehicle. It's a subset of this vehicle wherein I'm taking the rows that are there as a part of the train and all the columns. Test data, I'm considering those rows which are not there as a part of the train, all others except the ones that are there as a part of the train and all the column. So I have my training data as well as testing data with me. So this step is done. Now I am ready to estimate the model using the boosting process. So I can set some of the things. So let me use the boosting part. Let me simply call it as fit, right? So that we can use the other ones also here quite comfortably. We are using boosting. The formula that we are using is we require our dependent variable, which is class tilde. All other variables are my attributes or explanatory variables. So I am setting them. Data for me is the train data. I would be using the training data for building the model. Then what else do I require? The boost equal to true by default. So there is a bootstrap sample that is being taken. M final I can set it to 100. So I don't want to touch that. Right, and control, coefficient of learning, I will set it to zoo. By default it is Brahman. So that's where I want to set it to zoo, so that the initial SAME algorithm would be executed. And control, I can simply set it to rpart.control, the default one itself. rpart.control without any kind of modifications to it, right? So I can very well fit the model. This is my SAME model that is typically fitted. It's better that I save this so that I can make the changes necessary, and I can simply launch the other two models as well. So once the model is fitted, I will try to copy this formula and save it into a notepad, so that I can just make the change to the coefficient learning later, which would result in fitting a new model altogether. So let me copy this. Okay, this is the code for fitting a SAME algorithm using the boosting method. Now based on that, if I am looking at what is coming out of it, let me see what the fit is giving. There's a lot of information that is being given by the fit. Right, this fit has executed and given us so much of information. You could see all the splits are being showcased to us. That's a very big, so you could see, so for the number of training data, it has done the tree split across each of the cases. The splitting of the tree based on the various attributes is being performed across. Right, tree number 59, all the tree details have been provided. 364, 373, 382, 395, all the trees have been provided. Based on that, the weights that are associated are simply computed, and the votes to each one of them, weighted votes, are typically computed, based on which it will do the classification of all the three classes. So in some cases you see more votes have come to this particular class, in some cases more votes are lying here, in some cases the more votes are lying here. So the weighted votes to each of the classes are typically coming out, and based on that the probability are computed, the probability of belonging to each of the class are typically computed, and based on that the classification into each of the classes on the training data is computed. And you could also see the importance that is given to each of the variables, right? You can say $importance and you can very well access it. I see that distance circularity is having this much of weightage. Maximum length aspect ratio is carrying a much heavier weightage. scatter ratio and the maximum length aspect ratio are typically carrying much higher weightages compared to many other variables, right? And you could see skewness minor axis is something that is carrying the very least amount of variance. And I could see, so this is how the computation has occurred. And we could simply see that, yeah, 147 of them are classified as bus, 151 sub, and 146 are the vans from the actual data. Now, I really want to see from the actual data, from the training data, I want to come out with a table, right? So here we had a fitted model. So I will say from the fitted model, I am taking the class which is like a predicted values on the training data, and the actual training data I will take it from train data, the 7th column or the 15th column of the train data, which is typically the class. So I will take the table from here where I am getting the confusion matrix on the training data. This is the confusion matrix with respect to the training data. All arguments must have the same length. So if I look at train data, yes, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15th column itself. Let me say train data dollar class otherwise. Or let me see what is coming out in fit dollar class first. Oh, there is nothing that is coming out, right? Because what is there in fit? Fit dollar importance, oh, fit dollar class, small letter. Okay, when I say fit dollar class, so this is the fit dollar class. Okay, let me go back to do the table again. So I will say fit dollar class versus train data 15th column. So you could see that it's a perfect training that has happened, right? 147 buses are correctly classified, 157 subs are perfectly classified. So I could see that there's almost a full level of accuracy that is coming out in terms of the classification. So it might be because of overfitting of the model also. Here we are getting a much higher levels of accuracy. Probably the error rate is 0 in this case when I am going with the fitment that is coming from my on my training data, where I have looked at fit dollar class as well as the actual data that is coming from training data. It looks like the error rate is 0, means it's a perfect fitment of the model, right? So if you see here, we have estimated the model using boosting. We got a table of predicted and observed values, and based on that, when we looked at the error rate on the training data, it looked like 0% is the error rate. So now the doubt that I am going to get is there any kind of overfitting that has occurred to the data? But before we try something on the top of it, all these various things we can look at on the fit dollar trees. I can see to see what is coming out in the process. So all the trees, the different trees that came out, all the 100 iterations, we are able to see all the 100 trees that have come out in the process by doing fit dollar trees. Now I can say fit dollar weights to get what are the weights that are associated to each of the iterations. Now that we have 100 iteration, based on the result that each of the iterations have given, some of them have are given more weight and some of them are given less weight in terms of the final selection process. We see some of them carrying 3 point something, whereas some of them are in their twos itself. So each iteration is given a different weight, which we could see here. And now when I say fit dollar votes, I could see what is the weighted votes that each of these are getting. Each of the classes are getting, what is the weighted votes that each of the classes are getting, which we would have got using fit dollar votes. The same thing converted into probabilities, I can get it to fit dollar probability, each of them. And fit dollar class is giving me the class to which each of these elements is assigned, and fit dollar importance is telling me the importance associated with each of the attributes. So all these things we can very well look at. So that's the next step. So we had looked at all these things on the fitted model, and we got some kind of clarity regarding the outputs associated. But now that we have gone with 100 iterations, I really want to know how many iterations are very much optimal, right? Or I really am more interested in looking at the cross validation. Here it is having 0 as the error on the training data. So I want this process to be repeated n number of times. That is where I am performing 10-fold cross validation. This kind of cross validations are being performed through a function like boosting.cv. Let me just see the boosting.cv function, what it typically contains. So run n-fold cross validation with AdaBoost or SAP. Data is divided into, now what is happening here when I am saying v-fold, the data is divided into v non-overlapping subsets of roughly equal size. So now our data which is I can give the entire data also here. Why only the training data, right? I can give either the training data or I can give the entire data also. In the 10-fold cross validation, what happens is the whole data is split into 10 non-overlapping groups. Almost each group will have equal size. And the boosting is applied on the 9 subsets. So the 9 subsets will become my training data. The boosting is applied on all the 9 subsets. Prediction is done on the 10th subset. And this is the way 10 times the process is repeated. And based on that, we are trying to see what is the error that is coming out of the process. So this is where the boosting.cv, right? So that's where I'll use fitcv as the name of the method, which is using boosting.cv, for which I have to give the formula again, which is class tilde dot. Then I have to specify the data. So I can give the full data also. Why only the training data here? I can give the full data, which is the vehicle, or I can give only the training data also. Doesn't matter. Let me give only the train data. Let me see how it works. The same data, I am giving the train data here. Then it is talking about V, which is the V-fold cross validation. So if I am doing 10-fold cross validation, I can retain this V equal to 10. Boost equal to true, talking about the bootstrapping that can occur. M final, the number of iterations, we can set it as the same 100 itself by default. And the control, I can set it to be the same, rpart.control, right? But the default rpart.control I can still maintain. And coefficient for learning, I am talking about it as zoo. So all other things are the same, except now we are doing a 10-fold cross validation of the process. Okay, this whole thing on the same data, we are looking at the 10-fold cross validation of the process. With 100 iterations executed 10 times, which means 1000 iterations are typically being built, so that's where some amount of time involved in the process. So in the meanwhile, I can simply type out the steps. So we are taking a table of train data dollar class, which is the actuals, and fit dollar class, which is the predicted, for which we can typically see the confusion matrix. Right. So that's the second step after the boosting. We are doing that particular step as the second step. Based on that, we would have computed the error part. Then we are doing the fit CV, which is where we are doing the boosting part. I mean, we are doing a cross validation. So we are using the function boosting.cv, wherein I am providing class dollar tilde, I mean tilde dot data equal to train data, v equal to 10, m final equal to 100, which is the number of iterations we are setting to 100, control equal to r part dot control of the base itself, and we are saying coefficient of learning coefficient, we are setting it to zoo. So this is what is going as a part of our mod. Let's see whether this is executed. Okay, we are seeing that the 5 iterations have been performed. Alright, now it is clear that it has taken some time, started at 9:33, ended at 9:37, so almost 4 minutes it has taken to complete the fitment process. So now what it typically takes is, now I can look at what is going as a part of this fit CV. Now this fit CV, one, it is doing the classification part. Right, for each one of them it is doing the classification part along with a confusion matrix also it has provided. So the confusion matrix now with the cross validation 143, 135, 141. So now it looks like the error rate is to the extent of 5.6%. It was not exactly it's not exactly 0%, which was the case earlier. So I should better trust the cross validation error. This should be a much better reflection of what we can expect when we are doing the same on the testing sample, right? So this is one thing that I can very well look at. So the cross validation error is coming out to be around 5%. Now let me see if I do the testing, what would be the case. So when I am going with the testing, I am doing a predict. So here we would be using a function called predict.boosting. For the testing purpose here, we will use the function predict.boosting, not the predict function. So we'll see what it actually contains. So it classifies the data frame using a fitted boosting object. Right, I am just giving a fitted boosting object, that's it. All other things are same as your original predict model itself. So I am simply saying predict dot boosting. The input that I am taking is fit, right, or I can take fit CV, or I can go ahead with the fit itself. So let me see if I am giving fit CV. Right, fit CV is only for the cross validation purpose, but let me just check if I can give it. Then I am giving the new data as the testing data, test data. when I am giving that, no, I have to give, I cannot give fit CV as an input out here. I have to give the fit. So based on that, the prediction is being performed. When I am looking at the pred, it is again giving me the probabilities that are associated with each of the classes. It gives me all those calculations that we have got earlier also. The votes, the weighted votes that are going to each of the classes. Then the probabilities that are associated to each of the classes. And it also gives me the classes, the classification to each of the classes, as well as the confusion matrix, and the overall error rate of the model is around 6.8%. So the almost 93 to 94% is the accuracy of the classification of the value, even with respect to testing data. And what we could see is this number is much closer to the tenfold cross validation error that we have got earlier. So that's the reason we rely on the cross validation, so that it almost reflects the reality of if we want to execute it on the test data, what would be the numbers typically be looking like. So that is what is the accuracy associated with this model. Right on the test data I can write it. So this model has given me an accuracy of 6.84% when I am doing it on the testing data. Now here, just for the sake of steps, right, we have got the fit CV, we have done the cross validation and we have looked at it, and we are also doing the prediction, where we have done predict.boosting is the name of the model function that we have used, using the fit, where our new data is equal to the test data. That's it. And based on that, we have simply gone ahead with respect to looking at the model. So these are the 4 steps which are primarily there as a part of this particular SAME algorithm, which has resulted in a 6.84% error on the testing data as well. So that is how the binary is, that is how the multi-class boosting has actually helped in terms of prediction. Now let's look at the next model, which is the Bryman's extension for doing the same process. As I have already said, everything is the same. Loss function is exponential loss function. It assumes alpha m is half log 1 minus error divided by the error associated with each iteration. And difference is in the coefficient learning, we will set it to Bryman. Rest all is the same as what we have used as a part of the SAME algorithm. So the only thing is I can check the errors with respect to SAME. Right, even when I did a cross validation, what was the case? Right, cross validation also, it's better that if I do it with setting a seed, it would have been much better, but that's okay. So 5 point something was our cross validation error, and on the testing data the error is around 6.8% here. So let me try executing the same with respect to the Bryman algorithm. So I would be changing the coefficient, learning coefficient method. I will change it to Bryman. Rest all, I'll keep them to be the same, and I'll execute these 4 steps. So there is nothing much for us to learn in the process, only comparisons across the various algorithms, but wherever required I'll try to pitch the learning part. Okay, we are fitting a model. The Bryman's extension is what is now we are fitting to the data. Right, let's see would there be any kind of an improvement. So there in the SAME algorithm, the training error was almost 0. So all 100% were accurately classified on the training data. But here let's see what is the situation. Okay, the model is fit, and if I look at the model, again we are getting so many such kind of stuff which we are not, we can very well go and interpret each one of them separately. So some of the important things that we have used earlier also, We can very well use all of them to have a quick understanding. Fit dollar weights is something which I can look at to understand the weights associated with each of the groups. So we have seen some of them with zeros, within zeros, and some of them given weights in 1 plus. Similarly, the votes can give us, dollar votes will tell us which group got how many weighted votes, probability, the class. So I can very well say fit dollar class, which can give me the classes associated with each of the variables based on the train data. So if required, I can very well do the confusion matrix on the training data. Wow, even this model is nowhere lesser. On the training data, I could see that the error is almost zero out here as well. It's a 100% accurate classification on the training data. So the data is trained so heavily. That is what could be a disadvantage with the boosting algorithm. Now you could see, I want to change this. Now I want to now bring in the tenfold cross validation, and I am executing this piece of code to bring in the tenfold cross validation of the model. So I know that it will take around 3 to 4 minutes. So let me just pause the recording for this until this execution happens. So this is how it has executed all of them, right? And now I can look at the fit CV to really see some of the interesting things. The misclassification rate is around 6.7%. On the confusion matrix is 142, 131 and 45 are correctly predicted, resulting in a 6.75% error rate in the process, right? And I can look at the variable importance. I did not look at that variable importance, so I could go with fit dollar importance, and probably if required I can do the sorting on it directly so that I get the top 3 or in the order. So I'll do a sorting where I'll set descending equal to true, right, or decreasing equal to true. So I'll get it in the decreasing order or the descending order. So I could see here also the maximum length aspect ratio is the most important variable, right? Let me just even capture this as a part of the code. This I can do even before the boosting process, the cross validation process. So the maximum length aspect ratio comes out to be the highest impacting, scaled variance minor axis being the next one, the scatter ratio being the next, but again the skewness minor axis and scaled radius gyration being those variables whose impact is much lesser on the classification. So this is what has happened when we have looked at the tenfold cross validation. 6.7% is the error in the process. Now I can even go ahead with respect to do the prediction on the test data for the same model. And when I look at the pred, it looked like the error on the testing data is to the extent of only 6.31%. So this algorithm, right, this algorithm has resulted only in 6.31% error on the testing data, whereas SAME was giving 6.84% error on the testing data. A little bit of change with respect to the misclassification part. Now I would like to see how Freund's adjustment could have either improvised or decreased the forecast or prediction for us. So the only difference again is the iteration specific coefficient is, instead of half of that which was there as a part of the Bremen, here it takes log 1 minus epsilon m by epsilon m. That would be the iteration specific coefficient. Apart from that, everything is the same. In the coefficient learn, we are setting it to Freud. All else we are maintaining it to be the same. So which indicates that here I will make a change from Bremen, I will change it to Freud. Now let me go ahead in terms of seeing if this model can do any kind of betterment for our overall prediction of the class of the vehicles. So the fitted model, okay, the model is fitted. Let's see how good is this particular model on the training data. Right now we could see that it has done the computing more or less in a similar manner. So only when I make the table between the observed and the actuals on the training data, even this model is nowhere lesser, resulting in 100% accuracy, the error rate being 0. Looking at the variables and their importance, probably again the maximum length aspect ratio is given the much more higher weightage. Scatter ratio comes second here. Maximum length rectangularity comes third, whereas scaled variance minor axis, which was second in the earlier model, came to the fourth position. Skewness minor axis and scaled radius gyration, they are the ones that are there on the bottom two, even in the earlier algorithm as well as here as well. Now I would like to make sure, I would like to have a better assessment of the model, so that's where I want to perform the boosting on it. The cross validation on it. A tenfold cross validation is something that I am choosing. So based on that tenfold cross validation, I would like to assess what is the goodness of this particular model. What would be the typical error rate that this model is giving, which should be more or less in line with the error that we get on the testing data. So we should try out what is the kind of error that is coming out after the cross validation is performed on the training data. Okay, now that the execution is done, let's see what is the outcome that has come out. Now on the training data, the tenfold cross validation error is coming out to around 5.8% here, which looks like it is slightly lesser than what we have got in case of Bryman's extension. So here we want to see if when we are doing it on the testing data, is there any kind of an improvement in the overall process. I could see the buses wise, out of the 147, 142 are correctly predicted. Vans out of 146, 143 are correctly predicted. Some small error is existing with respect to the SAP itself. But let's take the prediction to the testing data to see is there any kind of an improvement. Now here it looks like the error is to the extent of 8.42%. With the Freund's adjustment on the test data, the error is coming out to 8.42%. But now when the comparison is only between these three, I could see that the Bryman's extension has really given me the least possible error overall, right? Doing the classification more and more appropriately, whereas the Freund's extension has given me an error to the extent of 8.42. But that need not be the case again for all kinds of data sets. Now this is where we would like to have a knowledge of all the various processes, and based on that I would like to see which one is giving me the least possible error on my testing data, so that I could use that specific model for my prediction purposes. So I would like to go with both one using the cross validations, two using my testing data, or I could even try out going ahead with advanced matrices like kappas and ROC curves, etc. as well. So those are different ways of assessing the goodness of the models. We can try all those models as well. But here, to get a good understanding of the multi-category based boosting, I thought I should look at these three models for you. see how we can execute all of them using the Adabac package using the boosting function, and identify and indicate the kind of differences that are existing between each of the different algorithms. I hope you got a good understanding of using these things for the prediction purposes. If you have any further clarifications regarding the same, you can very well get in touch with me by giving me a call on the number that I have given below, or you can even send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.